Hey everybody, welcome to number theory lecture number 15, I think. I think it's 15. Remember we ended up last time with a theorem and a proof that was rather interesting. The consequences of the theorem are definitely interesting. And the proof was really interesting because it's a really simple and intuitive proof. The theorem states that given any natural number n, there exists a sequence of n consecutive composite numbers. And n can be as large as we want. N could be a million, billion, trillion, quadrillion, and there's a sequence of a million, billion, trillion, quadrillion consecutive natural numbers that are all composite, which means that the greatest prime before that sequence starts and the least prime after that sequence ends. Two consecutive primes are a million, billion, trillion, quadrillion integers apart. The difference between them is at least a million, billion, trillion, quadrillion. And so the natural conclusion that we would draw from that, kind of a knee-jerk conclusion, is that pick any number. I won't say it that way. Take the kth prime number. Big prime number, but piece of k, the kth prime number. Based on what we just said, it's reasonable to conclude that there's no telling how far we have to go before we encounter the very next prime, piece of k plus 1. I mean, if we can construct a sequence of a million, billion, trillion, quadrillion consecutive composite numbers, then given the kth prime number, let's say it's a really big one, that there's no telling how far we might have to go before we encounter the k plus first prime. And that's a reasonable conclusion to draw from this fact that we observed at the end of the last lecture. And interestingly enough, that conclusion is not quite true. Given the kth prime number, it turns out that there is a limit as to how far we can go before we have to encounter its immediate predecessor, the k plus first prime number. And that fact, and we'll talk about it today, seems to be incommensurate with what we discussed in the last lecture. In the last lecture, we said, pick a natural number. Don't care how big it is, a million, billion, trillion, quadrillion. We can create a sequence of that many consecutive composite numbers, which means that the greatest prime number before that sequence starts and the least prime number after that sequence starts, two consecutive prime numbers have to be at least a million, billion, trillion, quadrillion units apart. And that's true. Well then, given the kth prime number, let's say it's a really big one, is it reasonable to think that there's no telling how far we have to go until we hit the next prime number, piece of k plus 1? And what we're going to look at today is a theorem and a proof that tells us, given the kth prime number, no matter what k is, there's a limit as to how far we can go before we hit the k plus first prime number. There's a limit to how far we can go, and it may be a pretty long ways, but there is a limit to how far we can go before we hit that next prime number. Okay, let's get on with our first lemma. This is something that we might actually know already. Let's take the finite geometric series, which means that each term after the first is equal to some constant times its predecessor. We're going to call that R, the ratio. And remember, that is the characteristic of a geometric series, whether it's infinite or finite. Each term after the first is equal to the ratio R times its predecessor. So this term is R times 1. This term is R times R squared. This term is R times R squared, R cubed, and so on. A finite geometric series, each term after the first is equal to the ratio times its predecessor. And the claim is that if we add up the terms from 1 to R to the n minus 1, this is what we get. And there are a number of ways that we can do this. I think we actually did this one by induction early on in the course, but let's do it a different way now. This is a proof that we can reuse at times to prove other things. And it's kind of a clever proof. It goes back to a mathematician called Gauss. I'm not sure he used the proof to prove this particular claim. When he was about 5 or 6 years old, he used the proof to show that the sum of the first 100 natural numbers was equal to 100 times 101 over 2. So I think what that is 50-50, 50-50. He was 5 or 6 and in with a bunch of 8 and 9-year-olds, and his teacher gave them this exercise to do to keep them quiet, for about 20 or 30 minutes while the teacher did other necessary things that they had to work on. And within maybe 20 seconds after the teacher assigned the class, little Gauss raises his hand. The teacher says, yes. And he shows her the number on his little slate, 50-50. What's that? Well, that's the sum of all of these numbers. Some people are just hardwired up here a little bit better than all the rest of us. And Gauss was one of those people. He's the first person to be known to use this type of a proof. And yeah, he did it when he was about 5 or 6 years old. But this is a great proof. We could use it to prove other things. So it's worth seeing. We have the sum from 1 to R to the n minus 1, and this is what it equals. Here's the proof. We're going to give a name to this sum. We're going to call it S. So S equals 1 plus R squared, dot, 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 all the way to R to the n minus 1. Now, take this equation and multiply both sides by R. R times S, RS. R times 1 is R times R is R squared, and so forth. R times R to the n minus 1 is R to the n. Now, here's what we do. We subtract this equation from this equation, and we write it down here as so. S minus RS on the left. 1 minus 0 is 1. R minus R is 0. R squared minus R squared is 0. Dot, dot, dot. R to the n minus 1 minus R to the n minus 1 is 0. And up here we have 0 minus r to the n. So s minus r times s is equal to 1 minus r to the n. And I'm going to have to erase the board. Okay, so this is what we ended up with. S minus r times s is equal to 1 minus r to the n. We'll factor out an s on the left side, and then divide both sides by 1 minus r. And we get that this sum s is equal to 1 minus r to the n over 1 minus r. And if you have a poor short-term memory like I do, this next step is important. We want to remember what it was that s was equal to. S was the sum of the first n terms of this finite geometric series. So we'll just make this substitution for s. And this is what we set out to prove. All we did was take this and substitute it in for s. Now, when Gauss was 5 or 6, this was not the proof that he did with this technique. He just added up the first 100 natural numbers, but he used the same trick. And yeah, 30 seconds later, yes, Gauss. Here it is. But this is the kind of trick that we can sort of incorporate into our mathematical repertoire of skills. And if we're going to do well in math, that's something that we need to do. We can't reinvent the wheel constantly. What we do is we take for granted that somebody else has reinvented the wheel and we use it to do other things. And we shouldn't have to reinvent the wheel to do all that we want. And I may have said this in this course before, and if I have, bear with me because it's an important observation. Isaac Newton, he invented calculus, and it was a major accomplishment, but probably not his greatest accomplishment. He did a lot of things, milestone things in physical science, astronomy, things having to do with calculation of orbits and orbital velocity as a function of the distance of the thing that's orbiting from one of the foci of its orbit, and so forth and so on. He was, without a doubt, the Einstein of his century, so to speak. But what he said about himself was, if I have seen greater than others, it's because I have stood on the shoulders of giants. And in saying that, he was acknowledging that what he had accomplished essentially was the culmination of all the work that those who had come before him had done. Now, he still had to be smart enough to put it all together, but he acknowledged that what he had done was the natural culmination of everything that everybody that had come before him had accomplished. He invented calculus, differential calculus. What is the motivation for that? We want to compute the slope of a line tangent to a curve. His mentor at Cambridge was somebody named Isaac Barrows, who spent the great part of his career studying tangents. So he definitely stood on the shoulders of his mentor, his advisor. And before him, somebody else had come up with limits, and somebody else had come up with essentially the XY coordinate system, the Cartesian plane, Rene Descartes. If we didn't have this XY coordinate system, then we really couldn't conceive of computing the slope of a line tangent to y as a function of x, and so forth and so on. So Gauss is the first person known to have used this sort of strategy to do a proof. And granted, he was only 6 at the time, but that shouldn't intimidate us. Maybe he wasn't completely human. Maybe he was like the hybrid offspring of a human and a space alien. Who knows? There are just some people, a handful of them in every generation that just seem to be quantum leaps more brilliant than all of their colleagues. And Gauss was definitely the Einstein of his century, too. And for the rest of us mere mortals, we shouldn't be intimidated by it. As long as we're good and we do our best, there's a place in math for us. There definitely is a niche, a place where we belong, and a place where we can make meaningful contributions. In math history, I talk about Eratosthenes. I think I talked about him in the last lecture. All of his colleagues called him beta. He wasn't an alpha mathematician, he was a beta mathematician. And yet his contributions to math and science and geography and other areas are well known today. And not only are they well known, they're marveled at because of his creativity and ingenuity. His colleagues didn't think he was an alpha, but he was good and he did his best. And there was a place for him in math at that time, and a place in academia for him at that time. Not only that, his work and the remembrance of his work has survived more than 2 millennia. So, hey, if we're not an alpha and we're a beta, that's okay. As long as we're good and we do our best, there is a place for us and we will make very meaningful contributions. Now, I'll get off my soapbox and we'll do some more number theory. Remember, what we're setting out to prove is that if we take the kth prime number, there actually is a limit as to how far we can go before we have to hit the next prime number. Everybody, here's the lemma that we just proved. Now we're going to look at a special case where r is 2. So we have 1 plus 2 to the first, 2 to the second, 2 to the third, 2 to the n minus 1 is equal to 1 minus r to the n over 1 minus r. But 1 minus 2, even I can figure out what that is. Just negative 1. So we're dividing this mess by negative 1, which means that what we really get is 2 to the n minus 1. So if we add up the first n powers of 2, where 2 to the 0 is the first power, and 2 to the n minus 1 is the nth power, so to speak, or let me say if we add up the powers of 2 from from n equals 0 to, I'm slaughtering this, I apologize. If we add up the first n powers of 2, starting at 2 to the 0 and ending at 2 to the n minus 1, that adds up to 2 to the n minus 1. And we're going to use this to put a bound on how far apart the kth prime and the k plus first prime can be. And also to put a bound in general on how large the k plus first prime can be. We're on our way. This is our first lemma, and it in itself sort of puts a bound on how big the k plus first prime can be. But we're going to use this to put a bound on how large the k plus first prime can be, a bound that's independent of all of the primes that came before the k plus first prime. So this will give us a bound in itself, but notice here it says this is a lemma and not a theorem. So even though this is a good result, we're going to use this to get a better result that's going to be independent of what the first k primes are. And here's what it says. Suppose P1, P2, P3, Pk are the first k prime numbers, and they're ordered according to size. So P1 is the least prime number, P1 is 2, P2 is equal to 3, P3 is equal to 5, P4 is equal to 7, and so forth. First prime number, the least prime number, the next least prime number, so forth and so on, the greatest of the first k prime numbers, and this is going to be the first prime number after the first k prime numbers. So here are the first k prime numbers ordered according to size, or maybe the first k plus 1 prime numbers ordered according to size. The k plus first prime has got to be less than capital P, where capital P is the product of the first k primes plus 1. So we take all of the prime numbers in order of size, P1 being the least prime number, period, and Pk plus 1 being the greatest of the first k plus 1 primes. The k plus first prime number is less than or equal to P, where P is the product of the first k primes, plus 1. Okay, let's begin our proof. Okay, let's get on with the proof. Let's refresh ourselves as far as what these things are. We have the first k prime numbers, actually the first k plus 1 prime numbers, listed according to size from least to greatest. P sub 1 is the least prime number. P sub k plus 1 is k plus first on the list from least to greatest. And we're trying to prove that this guy, the k plus first prime number, is less than or equal to P, where P is this thing, the product of the first k prime numbers plus 1. We're going to do this proof by contradiction. We're trying to prove that the k plus first prime number is less than or equal to this number P, which is the product of the first k primes plus 1. So for the sake of deriving a contradiction, we assume the opposite. The k plus first prime number is greater than this number p, which is the product of the first k primes plus 1. And we're going to make two observations. According to our supposition, this thing, all of the natural numbers below, that is, all of the natural numbers listed right here, are composite. Well, let's see. Let's make sure we understand what this thing is. This is P. And so, according to our supposition, the k plus first prime number is greater than P, this thing. And the kth prime number, p sub k, is less than p sub k plus 1. So what have we actually constructed here? We've constructed a sequence of consecutive natural numbers starting at p sub k plus 1, where p sub k is the kth prime number. And the sequence increases in increments of 1. Take this thing, add 1 to it. Take this thing, add 1 to it. Take this thing, add 1 to it. And we keep adding 1 to each term in this sequence until we arrive here. These are consecutive natural numbers, and we claim that they're composite. Well, why can we conclude that? Notice that p sub k is less than this thing, because this thing is p sub k plus 1. So the kth prime number, p sub k, is less than every single number on that list. The least number in this sequence is p sub k plus 1. So the kth prime number is less than this thing. And we've assumed, for the sake of deriving a contradiction, that the k plus first prime number is greater than this thing, right here. The k plus first prime number is the next prime number after this guy, and it's greater than this thing. So the kth prime number is less than the smallest natural number on this list. The next prime number, p sub k plus 1, we're supposing is greater than the largest number on this list. Two consecutive prime numbers, p sub k and p sub k plus 1, according to our supposition, p sub k plus 1 is greater than that thing. So yes, all of these numbers have to be composite, because the kth prime number is less than the smallest number in this sequence, and the k plus first prime number is greater than the largest number in this sequence. And how many prime numbers are there between the kth prime number and the k plus first prime number? None. So all of these numbers have to be composite. That's the first observation that we make. Our second observation, none of the first k primes, p1, p2, p3, pk, none of the first k primes are divisors of this number p. Now, how on earth do we know that? Well, let's see what would happen if one of these guys actually did turn out to be a divisor of p. Okay. None of these primes, none of the first k primes are divisors of p. Why not? Well, let's see what happens. If one of these guys, let's say p sub I, where I is between 1 and k, if one of these guys, p sub I, actually divides p, well, this is also going to be a divisor of the product of primes from p1 to pk, because p sub I is one of the factors in this product. Okay. So p sub I divides p sub I divides this thing, which means that p sub I divides every linear combination of this thing and this thing. P sub I divides every linear combination of p and this. In particular, p sub I is going to divide p minus p sub 1, p sub 2, dot, 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 p sub k. But wait a minute. What is capital P? Capital P is this thing plus 1. So the difference of these two things is just 1. And that can only happen if P sub I is equal to plus or minus 1. What's the problem there? Look, what's the problem there? If P sub I is equal to plus or minus 1, then P sub I can't be prime. Prime numbers are greater than or equal to 2 because prime numbers have to have two distinct positive divisors, namely 1 and itself. 1 has only one distinct positive divisor, and that's 1. So the fact that P sub I turns out to be plus or minus 1 contradicts the fact that P sub I is prime. Okay. So This is trivial stuff. You don't need to see me writing it. Okay, let's clean everything up and finish this off. Remember, we got a contradiction. Now, what caused the contradiction? Since the assumption that the k plus first prime is greater than p, where p equals the product of the first k primes plus 1, this is the assumption that led to the contradiction. So since this assumption leads to this contradiction, or maybe I should say a contradiction, the assumption has to be false. This assumption, which leads to a contradiction, has to be false, which means that the k plus first prime has to be less than or equal to the product of the first k primes plus 1. So see right there, we've come up with a limit as to how large the k plus first prime can be. Now this limit, or this bound on the k plus first prime, is given in terms of its predecessors. It's a very useful theorem or lemma. If there's anything that is lacking in it, it's the fact that it does depend on a knowledge of all of its predecessors, the first k primes. So we have a bound on how large the k plus first prime can be. It's given in terms of all of its predecessors. What we're going to do next is take this result and create another bound that's independent of a knowledge of what the first k primes are. The next bound that we come up with is not going to have any of these primes in here. It's going to be given just in terms of an integer, a natural number. Here's our theorem. If p sub n is the nth prime number, assuming that the prime numbers are ordered from least to greatest, if p sub n is the nth prime number, then p sub n is less than or equal to 2 to the power of 2 to the n minus 1. And we prove this by strong induction. Here's our basis step. P sub 1, the first prime number, is equal to 2. We know the first prime number is 2. And 2 is less than or equal to 2 to the first, which is equal to 2 to the power of 2 to the 0. 2 to the 0 is 1. And 2 to the 0 is equal to 2 to the power of 1 minus 1. Well, guess what? This is written in that form. Essentially, we have p sub 1 less than or equal to 2 to the power of 2 to the n minus 1, where n is equal to 1. This is less than or equal to that for n equal 1. So this is our proposition evaluated at n equal 1, and n equal 1 is true. Okay, now for the induction step. Okay, now for the induction step. Suppose that our proposition p of n is true for n equal 1, 2, 3, all the way up to k. Now we're going to show that this means that p of k plus 1 is true. Well, let's see. Suppose that p of n is true for n equal You know what? I think I want to rewrite this. Forgive me, please. I like this better. Suppose that P of n is true for n equal 1 through k. We're going to show that P of k plus 1 is true. That is, P sub k plus 1, the k plus first prime, is less than this thing. We are supposing already, by strong induction, that P of n is true for the first k natural numbers. So for n equal 1, this is true. For n equal 2, this is true. All the way up to n equal k, this is true. And we're going to show that this thing is true for n equal k plus 1. Here's our piece of k plus 1. And that simplifies to this. See, k plus 1 minus 1 is just k. So the k plus first prime is less than or equal to 2 to the power of 2 to the power of k. That's what we're going to establish. Now, how are we going to get there? Well, by our previous lemma, the k plus first prime is less than or equal to the product of the first k primes plus 1. And here's where we get to use strong induction. The first prime, by induction hypothesis, this is less than or equal to 2 to the power of 2 to the power of 1 minus 1. See, this is just our induction hypothesis for n equal 1. And this thing, by the same induction hypothesis, is less than or equal to 2 to the power of 2 the power of 2 minus 1. And by the same induction hypothesis, this thing is less than or equal to 2 to the power of 2 to the power of 3 minus 1. And this thing, by the same induction hypothesis, is less than or equal to 2 to the power of 2 to the power of k minus 1. And let's simplify this. Forgive me, I don't remember before I stopped the video whether I started here and came up here or whether I have yet to discuss this. But anyway, by our induction hypothesis, P1 is less than or equal to 2 to the power of 2 to the 1 minus 1. By our induction hypothesis, P sub 2 is less than or equal to P to the power of 2 to the power of 2 minus 1. P3 less than or equal to P to the power of 2 to the power of 3 minus 1. And P sub k less than or equal to P to the power of 2 to the power of 2 to the power of k minus 1. So that tells us that P sub k minus 1 is less than or equal to 2 to the power of 2 to the power of 1 minus 1 times P sub 2, which is less than or equal to 2 to the power of 2 to the power of 2 minus 1, and so forth and so on. The k plus first prime is less than or equal to this monstrosity. Now, let's simplify. This is 2 to the power of 2 to the 0 times 2 to the power of 2 to the first times 2 to the power of 2 squared times dot 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 times 2 to the power of 2 to the k minus 1 plus 1. Okay, now let's see. Let me rewrite this again. 2 to the power of 1 times 2 to the power of 2 times 2 to the power of 4. Do I want to do that? Let's see. Do I really want to do 1, 2? Nah. Let me keep this as 2 squared. And let's take stock of what we have right here. We have a product of things raised to a power. In each case, the base is 2. So if we have a product of things raised to a power and the base is the same for each of the factors, what do the exponents do? They add, right? Like 2 to the first times 2 to the second is equal to 2 to the 1 plus 2. Well, we just continue this. We have 2 to the power of 1 plus 2 plus 2 squared plus dot 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 plus 2 to the power of k minus 1 that whole thing plus 1. Ooh. Have I seen this before? I sure have. I sure have. This thing from our lemma is equal to 2 to the k minus 1. So this whole thing is equal to 2 to the k, 2 to the power of 2 to the k minus 1 plus 1. And that I can just take this and add another one of these. It doesn't make sense other than just to tidy up what we have. In a more compact form. Now, what did I do? 1 is definitely going to be less than or equal to 2 to the power of 2 to the k minus 1. As a matter of fact, the only way that this thing and this thing are going to be equal is if k is 0, right? If k is 0, then this is 1 minus 1. The exponent's 0. This is 2 to the 0, which equals 1. This thing is equal to this thing when k is 0. When k is greater than 1, this thing is greater than that thing. So yes, this expression is less than or equal to that expression. And why on earth would I do that? Seems like I'm getting a higher bound than I need to by replacing 1 with this thing. But I'm also going to get a more compact form. I have this thing plus this thing. Oh, they're one and the same, aren't they? So this I can write as 2 times 2 to the power of 2 to the k minus 1. Well, let's see. This is 2 to the first times this thing. The exponents just add. So that's going to be 2 to the 2 to the k. Okay. I started here with the k plus first prime, and I've shown that it's less than or equal to this thing, 2 to the power of 2 to the k. But wait a minute. This was what we needed to show for the induction step. P sub k plus 1 is less than or equal to 2 to the 2 to the k. This is P of k plus 1. It's our proposition evaluated at k plus 1, and it is true. So we just finished the induction step. So now all we have to do is restate our proposition and assert it's no longer just a proposition. It is a theorem. Here's what we just proved, our proposition on n. If P sub n is the nth prime number, then P sub n, the nth prime number, is less than or equal to 2 to the power of 2 to the n minus 1 for all natural numbers n. This is a bound on how large the nth prime number can be. In our previous video, we saw that we could create a sequence of n consecutive composite numbers for any natural number n, even n equal to 1,000,000, billion, trillion, quadrillion. We can create a situation where 2 consecutive prime numbers are at least that far apart, and yet at the same time, given a specific prime number, like the P sub n, there is a limit as to how big it can be. The nth prime number can't be any larger than this thing. So those appear to be two incommensurate facts. Given a natural number n, there's a limit as to how big the nth prime number can be. And yet, given any natural number n, we can create a sequence of n units long, a sequence of n composite numbers, which means that there's at least a gap of n between the prime number that comes immediately before that sequence and the first prime number that comes after that. We can find a situation where two consecutive prime numbers are no closer than a million, billion, trillion, quadrillion, or whatever number we want to pick. At the same time, there is a limit as to how large the nth prime number can be. Whoever says that math is boring hasn't really gotten to know number theory.